So, welcome back to our lecture series on linear control system. So, today we are on the fourth lecture of module 1, and in the last class we discussed about modeling of a mechanical system. On that aspect, in that class we considered a translational system. Translational system means it is a system that moves in a linear direction. So, in that class we considered a mass attached with a spring, and we are moving it in a linear direction, and we developed the differential equation of force and its output displacement, and we converted it to, we identified that it was a first order differential equation, it was a second order differential equation, and we converted that to its transfer function by using Laplace transform. So, if anybody is having some doubts on that lecture, before going to the fourth lecture, you should be very clear about the concept of third video lecture, because the entire thing of force voltage analogy and force current analogy is based on that concept. Without having the concept of developing the differential equation of a mechanical system, you can't understand anything related to force voltage analogy and force current analogy. So, now we are starting into the details. So, this is for first topic I am taking as force voltage analogy. Before going to this, first of all I would like to comment something about what is condition for analogy. So, initially we are coming to the second heading, condition for analogy. So, what is condition for analogy? Analogy means we are telling about the two different quantities or two different physical phenomena, and these two are physically and placed in different domains. These two quantities or two phenomena are physically entirely different. But if we are developing the differential equation or modeling, if you are considering the modeling of the two different system, then the differential equation should be in same format. The order should be same. It should have identical identical coefficients and identical differential terms in each equation. So, condition for analogy is simple. The two systems will be physically different, but their differential equation should be of same format. So, in force voltage analogy, we are it is very clear that we are going to compare a mechanical system, that is something related to force, to a electrical system, that is something related to voltage. So, before going to this, you should be very clear about what is the differential equation of a mechanical system that we derived in the last class, and that was a translational system. That translation means it is a system moving in a straight line. So, it is written in the so it is written in the first line. Modeling of mechanical translation system was done in detail in the last class. Then here we are comparing the differential equation of a translational system with differential equation formed by a mesh equation or KVL equation of RLC series electrical network. That is the important point. RLC series electrical network. We are taking a RLC series electrical network. So, that is an important point. Don't to be confused. In the next analogy, that is force current analogy, you should be dealing with RLC parallel network. So, this point should be very clear. In case of force voltage analogy, you have to compare the mechanical translational system with a RLC series electrical circuit. RLC series electrical circuit. And one more point is there, RLC series electrical circuit is an electrical circuit which consisting of a resistance, inductance and capacitance, and these three elements will be connected in series, and this circuit is excited by a voltage source. As it is a series circuit, you have to give an excitation of a voltage source. In case of parallel circuit, in the next video, next class, we are using a RLC parallel circuit, and in that case, at that time, we will be using a current source. So, it should be very clear, and you should be very thorough about these things. So, we are comparing a translational system with a mechanical translational system with a RLC series electrical system, and this particular RLC series system is excited by a voltage source. Okay. So, I am going to next slide. Here, this is a brief recap of what we have done in the last class. If I have to model a mass and we are applying a force F, we are applying a force F like this, and then the system will, mass will move in x direction with a particular distance of x distance as shown in figure. So, then in this case, if we are applying force F on the mass to move it, it should automatically develop some opposing force that is known as Fm, and the equation of force, whatever F for Fm, is simply by Newton's law, it is mass into acceleration, m into a. In this case, as the object is moving to a distance of x length, length is marked in the figure, the object is initially here, and we are applying a force and moving this object to some distance, and this distance is x. So, x is the distance, then derivative of x, that is dx by dt, that is nothing but velocity, and d square x by dt square, that is derivative of velocity, that is nothing but acceleration. So, Fm, that is the force developed by the mass to oppose the applied force, Fm, that is nothing but the mass into acceleration. Mass is simply not as m, and acceleration is d square x by dt square. So, Fm is equal to m d square x by dt square. Next slide. We are considering a damper or dashpot. So, entire things are there in the last video. I am just refreshing it. So, dashpot is nothing but it represents the friction as we are moving on a plane. That plane should have a friction. That friction is represented by a component known as dashpot. And as we are applying a force F to move this object, the friction will impose another opposing force that is nothing but named as Fb. Here you can see it. That force is named as Fb, and that Fb is directly proportional to the velocity of motion. You are applying a force and you are moving the object, that object's velocity v. So, the Fb is directly proportional to velocity of motion, and if we are avoiding the directly proportionality by using a constant, then we can say Fb is equal to b into v, and b is nothing but frictional coefficient, that is a coefficient related to a damper or dashpot, frictional coefficient, and we can simply replace v. V is nothing but velocity, that is equal to a differential of displacement dx by dt. So, Fb is equal to b into dx by dt. This is the conclusion of the second case. Fb is equal to dx by dt. Okay. Mass and dashpot is over. Now we are dealing spring, and if we are connecting the mass with a spring, and then you are moving, or simply you have a spring. A spring is there in between the mass and the wall. Then if we are moving the mass, the spring will also stretch by some distance x. And if force applied, if we are applying a force F on the spring, automatically it will impose a opposing force, that is nothing but a spring's force developed by spring, that is Fk. Fk is directly proportional to the displacement. It is common logic. If you are extending a spring by some force, the opposing force will be directly proportional to how much distance you are expanding the spring. The opposing force will be directly proportional to the distance that you are expanding the spring. So, Fk is directly proportional to the distance x, and Fk is equal to k into x. K is nothing but spring constant. So, Fk is equal to k into x. Now, you got three forces. One is force corresponding to mass, other one force corresponding to friction, and third one force corresponding to spring. we are comparing these three things into a single figure. Now the mass is connected with a spring, and also the mass is having a friction effect that is represented by a dashpot. You can see dashpot here, it is friction effect, and spring is here. So as I have applied a force F here, this force will be affected on three components simultaneously. So the total force F of t is nothing but force of M plus force developed by B plus force developed by K. I am applying a single force and I am getting some displacement X. But the counter force is developed by the three components simultaneously. So applied force F of t is equal to sum of three counter forces, F of M plus F of B plus F of K. So in the last three slides I got what is F of Fm, what is Fb, Fk. So I am just simply substituting here F of t is equal to m d square xt by dt square plus b dx of t by dt plus k into x of t. Now everything is expressed as a function of time. That is only difference. D square, every force is also considered as a function of time, and displacement is also considered as a function of time. So with every f, I am not simply writing fx, I am writing f of t, x of t. That's all. So this is just a recap. If you are having any doubt on this topic, that is the development of differential equation of a translational system, please refer the last video. Okay, now we are coming to the new topics. We have to compare this particular system. We have to compare this particular system with an electrical RLC series circuit. Okay, so this is RLC series circuit excited by a supply voltage source V, and you can see here we are having three sources, three components R, L and C. So voltage across VR, voltage across resistor is marked as VR, voltage across inductor is marked as VL, and voltage across capacitor is marked as VC. What is VR? VR is nothing but I into R, current into resistance. What is the voltage across an inductor? It is nothing but L di by dt. And voltage across a capacitor is also a known. I think everybody knows these equations. These are the basic equations from electrical theory or basic electrical. So VC, voltage across capacitor, is nothing but 1 by C integral I dt. So these three are the known equations, and the total input voltage will be equal to the sum of VR plus VL plus VC, or we can simply write KVL equation. KVL equation means I am assuming a loop direction like this, and as the current is entering at this side, this terminal is marked as positive, and for inductor the current is entering at this terminal, so that is marked as positive, and for capacitor current is entering at this terminal, so that is also marked as positive. And if we are applying a KVL, that will give minus V plus VR plus VL plus VC is equal to 0. So nothing but you will get the input voltage V is equal to sum of the three dissipated voltages VR plus VL plus VC. Actually no need to apply KVL and all. You can simply write what the applied voltage is equal to voltage that dropped across three components. So V is equal to VR plus VL plus VC, and I am substituting VR is equal to IR and VL with L di by dt and VC by 1 by C integral I dt. I am substituting these three things. So now I got some equation. Okay. Now I am going to substitute in the previous equation. Current is nothing but rate of the differential of charge Q, I is equal to dq by dt. So instead of I am substituting dq by dt. So V is equal to R into dq by dt plus L into d by dt of dq by dt and 1 by C into dq by dt into dt, because previously it was 1 by C integral I dt. So I is substituted at dq by dt. So here we are having a dt also here. It is covered by the watermark. Okay. So add that dt also. So V is equal to R dq by dt, L d square q by dt square plus 1 by C q because integral of dq, dt will get cancelled, integral of dq is equal to q. So by rearranging the equation, we get v is equal to L d square. I am rearranging means I am arranging on the base of order. There is a second order term, first order term. So I am arranging in the base of that order. So v is equal to L d square q by dt square plus r dq by dt plus 1 by c into q. So this is the differential equation of RLC series system. And now it is time for comparing this differential equation of RLC series system with the already obtained differential equation of the mechanical system. So now we can compare this analogous equation. You can see in the black ink I have written the equations of an electrical system, and in the red ink I have written the force equation of a mechanical system. These two equations are almost similar in format. So I am marking the analogous terms. In the left hand side, I can simply say voltage is analogous to force. And the coefficient of d square q, d square term, that is nothing but L and M. These two are identical, that is mass is identical to inductance L. And the coefficient of dq, d by dt term, that is nothing but R and B. So R and B are also analogous. And the coefficient of constant, q is the variable in first case and x is the variable in the second case. So zeroth order term are having a coefficient of 1 by c and k. So I am comparing, so I am saying that k is analogous with 1 by c. So just comparing these two differential equations and we are marking the analogous terms. And also we can say as the variable in the first equation, q is the basic variable, and the second equation, x is the variable we are considering with respect to time. So q and x are identical, q and x are analogous. As q and x are analogous, we can say dq by dt is analogous to dx by dt. Just differentiating, as q and x are analogous, we are differentiating these both terms with time. So dq by dt is analogous with dx by dt. Okay, so if dq by dt is analogous with dx by dt, we can say what is dq by dt? dq by dt is nothing but current, and dx by dt is nothing but velocity. I think it is clear. dq by dt is differential of charge, that is current, and dx by dt is differential of distance, that is velocity. So we can add one more analogous statement, that is current is analogous to velocity v. Okay. So I am bringing the all conclusions into a single slide. In translation system, force, that is analogous to voltage in electrical system. Mass, that is analogous to inductance in electrical system. Frictional coefficient B, that is analogous to resistance in electrical system. Spring constant K, that is analogous to reciprocal of capacitance, that is 1 by C. And displacement X, that is analogous to charge, and velocity, that is analogous to current. I hope all these terms are very clear as per the last derivation itself. So you can conclude the entire analogous terms in a single table like this if this question is asked for any exams. And if this question is asked for a essay type question, you have to write the entire derivation and then you have to scrutinize the analogous terms in a table like this. Okay, now the second heading, that is force current analogy. So force equation is automatic. Already we have detailedly analyzed in the last class, and also we refreshed that force equation of translational system in this class also. So under this heading, force current analogy, I am not going to the details of the force equation, that is already explained very well. And the force equation of a translational system or the mechanical translation system is compared with RLC series system of electrical circuit. In the last case, we are comparing the force equation with RLC. Sorry, in the last case, we are comparing it with the RLC series equations. But now, we have to compare it with RLC parallel equation. And also one more change is there. In case of RLC series equation, you are considering a voltage source as excitation. I hope that point was already mentioned in the last heading also. At that time I said it clearly. In case of RLC series circuit, you have to give a voltage source as excitation. And in case of RLC parallel system, we have to give a current source as excitation. That is the other difference in force current analogy. Okay, so now we can go to a RLC series or RLC parallel system. Here a current source I is marked. You can see a current source I is here, and that is I is splitting into IR and IL and IC. IR is nothing but current in resistance R. IL is nothing but current in inductance L, and IC is nothing but current in capacitor C. But we know that these RLC both are parallel elements, and for any parallel element voltage will be constant. For any parallel element voltage will be constant. So that voltage is marked here like across these two terminals. So V is same across capacitor C, inductor L and resistance R. The voltage across the three elements are same and it is marked as V. So voltage is same in a parallel circuit and current will be splitting into different values in a parallel circuit. That is a conclusion you have to remember while going to this derivation. So nothing but it is very simple. We are directly applying Ohm's law. V is equal to IR. So current in a resistor I is equal to V by R. So IR is marked as V by R, where R is the value of resistance and V is the voltage across that resistance. And in the last case we written voltage across inductor VL is nothing but L di by dt. In case of current across capacitor is C dV by dt. Voltage across inductor was L di by dt. Similarly, current across capacitor is C dV by dt. And current across inductor is 1 by L integral V dt. All these are standard equations based on Ohm's law. If you are having any doubt, you can refer textbooks of basic electrical engineering. These all derivations are there in my channel also. You can refer the videos of basic electrical engineering. Module 1, you can refer the voltage and current equations of resistor, inductor and capacitor. So these are the standard equations. And now I can say the input current I is nothing but IR plus IL plus IC, because the I is splitted into three parallel paths. So I is nothing but sum of IR plus IL plus IC. Okay. Now I am substituting the Ohm's law expressions in that particular current equation. So IR is nothing but V by R, IL is equal to 1 by L integral V dt, IC is C dV by dt. And I have marked the equation number 1, it is here. The equation number 1 is marked here somewhere, it is covered by the watermark. So substitute in that equation, we are going to change the common variable V by substituting d phi by dt. What is phi? Phi is nothing but flux linkage. Phi is nothing but flux linkage, and that comes from Faraday's law of electromagnetic induction. EMF or voltage is nothing but the rate of change of flux linkage, that is stated by Faraday. So this is the statement, mathematical expression of Faraday's law. V is equal to d phi by dt and phi is equal to flux linkage, and we are substituting that in the equation number 1. So I will be 1 by R into d phi by dt plus 1 by L integral, instead of V I am giving d phi by dt into dt. Here it is. Okay. And C dV by dt is substituted as C into d by dt into d phi by dt. So instead of all voltage terms, I have substituted d phi by dt. Now we can rearrange the equation like you can check the equation in the green ink. So I is equal to 1 by R into d phi by dt plus 1 by L into phi, because dt get cancelled and integral of d phi is marked as phi, plus C into d square phi by dt square. And on rearranging this equation based on the order of differential terms, you will get I is equal to C d square phi by dt square plus 1 by R d phi by dt plus 1 by L into phi. So this is the final differential equation of a RLC parallel system. Now it is time for comparing the obtained equation with the equation of a translational mechanical system. Okay. So in greening, I have written the equation of electrical system, and in the red ink, I have written the force equation of a mechanical translational system. Now you can see both the equations are of same order, same format, same pattern. So you can easily point out which are the analogous terms. So easily I can say current, the left hand side current is analogous to force, and coefficient of second order term, d square term, is nothing but C and M. So C and M are analogous. Coefficient of first order term, d phi by dt and dx by dt I am comparing. So its coefficient are 1 by R and B. So 1 by R is analogous to B. And coefficient of zero order term, that is 1 by L and K. So 1 by L is analogous to K. And the basic variable is nothing but, in the first equation it is phi, flux linkage, and the second equation it is x. X is nothing but displacement. So phi is analogous to displacement, or flux linkage is analogous to displacement. So what are the differential of that terms? As phi is analogous to displacement, d phi by dt is analogous to dx by dt. d phi by dt is analogous to dx by dt. What is d phi by dt? d phi by dt is nothing but voltage. And what is dx by dt? That is nothing but velocity. Both are v. So don't just write v is analogous to v. Write in detail. d phi by dt is voltage, that is analogous to velocity, dx by dt. So we are concluding the entire analogous terms by scrutinizing them into a table. Translational mechanical system, force is analogous to current, mass is analogous to capacitance, friction coefficient B is analogous to 1 by R, spring constant K is analogous to reciprocal of inductance 1 by L, displacement X is analogous to magnetic flux linkage phi. Actually it is flux linkage phi. You can just simply write as flux also, but according to Faraday's law, with the in term of an electrical engineer's representation, you have to specify that it is magnetic flux linkage, and its differential velocity, that velocity is analogous to voltage. So this is the final table in which I am scrutinized all the analogous terms of force current analogy. So now we are done entire analogous comparison of force current analogy and force voltage analogy. So one point you have to be very clear that before trying to learn this analogy, you have to be very clear about the mathematical modeling concept, how we can modeling a mechanical system, how we can modeling an electrical system. Such things you should be very clear about. And then this analogy comparison and its differential equation comparison is very simple. Hope it is well understood. So we can meet in the next video. Thank you.